Hello again, everybody, and welcome to yet another review session for your final exam in Calculus 3208, our second last in the entire series. Wow, there's lots of them too. Okay, so today we're looking at, in Unit 8, still dealing with exponential and logs, we're going to talk about something called logarithmic differentiation and why we have something called logarithmic differentiation. And we're also going to talk about not specifically performing logarithmic differentiation today, well, not for many things anyway, but just sort of how we set things up to make that happen. And then in our last video, which is the next session, we'll talk about how do we actually do this logarithmic differentiation business. So we're going to look at something that I call the x to the power of x problem. It's a bit of a weird question, isn't it? X to the power of x, weird expression. And we're going to apply laws of logarithms to simplify differentiation. Simplifying differentiation would be nice, wouldn't it? Let's take a look. The x to the power of x problem. How do we differentiate f of x equals x to the power of x? Well, there's a couple of things that might come to your mind. And do as I say, not as I do here. Don't repeat this stuff. But what you might think is you might try f prime of x is, well, the first thing might come to mind would be the power rule, because you've got a base of x and an exponent. So you might say x times x to the power of x minus 1. Nope, can't do that, because in truth, because this exponent is variable, it's not just a power function. Okay, so then the next thing you might think is, okay, so it's an exponential function. Easy. So if it's an exponential function, then my derivative f prime of x, let's see, should be a to the power of x. So x to the power of x times ln x? No, that doesn't work either. We're not allowed to do that. It's not truly an exponential function because our base is also a variable. So what do we got here? We got a really strange function. We cannot apply the power rule because the exponent is variable. We cannot use the rules for differentiating exponentials because the base is a variable. Well, have no fear. We're going to develop a new differentiation technique to help us deal with this hybrid function that runs on both electricity and gasoline. No, sorry, it's not the same thing at all. So let's see. Solving the x to the power of x problem. Let's take the function y equals x to the power of x. We're going to perform logarithmic differentiation. Now, we had a sneak peek at this way back when we developed the derivative for y equals a to the power of x. But let's see how we get this one to work. What we're going to do is we're just going to apply the natural logarithm, ln, and we use that. You could use any base log really for this, but natural log is easier to compute things with. So we apply ln to both sides of the equation, and we get this. Okay? And the reason we like to use logarithms here is because now this exponent can play the floater rule game, or the power rule, or the multiplication rule, or whatever you call it, and it can end up out in front there. So now, if we want to try to differentiate the equation that we have, the right side is just a product rule, and we don't have this x to the power of x business anymore. The left side is a little more complicated than it used to be because it's a logarithm, and it's got a y there, so we're going to have to use implicit differentiation and apply the chain rule, but still it's doable, and it's not too bad. So let's take a look at that left side. The derivative of ln of anything is 1 over the anything multiplied by the derivative of what's in there. So that's just implicit differentiation. Okay. And then product rule on these two things over here. So the derivative of x is 1 multiplied by ln x, and then the derivative of ln x is 1 over x multiplied by x. So simplifying, that's just going to be 1 times ln, which is ln x, and 1 over x times x is just x. Or sorry, 1, excuse me. So now what I have to do is I have to get dy over dx isolated. So I multiply both sides of my equation by y. And when I multiply both sides by y, I get an equation that looks like this. Okay, that's pretty good. And then I don't like to have a y in my expression because I started with y just in terms of x. So I'm going to try and get the y out of there. So I'm just going to replace it with what I know y is equal to. And so there we have it. Just going to multiply through using distribution, or you can leave it in factored form. Either one of these is good enough. But we have a derivative for x to the power of x. Now, it's not a direct method like we had. It's not like there's a rule for always differentiate x to the power of x this way. No, we had to use this logarithmic differentiation. So it's kind of a way to sneak in the back door to get at that derivative. But that's where it is, so we're rolling along now. Okay. There is one other important application of logarithmic differentiation. And I think the best way to show it to you is to look at an expression or a function like this one. So let's say I have some function y equals, and it's going to be a combination of a whole bunch of other functions. So f of x times, and just as an example here, I wrote f of x times g of x squared, all divided by the square root of h of x times k of x. Now that's not a pretty looking thing. So if I wanted to try and take the derivative of that, and if I want to differentiate it, whatever way you want to say it, what do we have here? Well, in the biggest picture I have a quotient rule because of this fraction. And then inside the quotient rule, I'm going to have a product rule in the numerator and a product rule in the denominator. Each one of these things is its own function that's going to require a derivative of that as well. And I've got g of x nested inside a square, so that's a chain rule. And h of x is nested inside a square root, so that's also a chain rule. So what we have is two chains inside two products inside a quotient, or what? And that, believe it or not, we could do. We could do it with a sledgehammer, but it would take a long time. The other option is we can apply that technique that we just saw called logarithmic differentiation. So I just apply a natural log to both sides, and what that does is it allows me to separate all that business out. So on the left side I'd end up with log y. So I'd have to use implicit differentiation, true. But instead of differentiating a big conglomerated mess, all I have is just a log of each of the functions multiplied by constants. So it's just going to be 1 over each of them multiplied by the derivatives. And that's way easier than having to do all that other stuff. Then we still have to rearrange to get y or dy over dx by itself, but trust me, it'll save you a lot of time and effort. We are not, however, going to go all the way through with logarithmic differentiation on such functions in this session. What we're going to do is we're just going to do some practice, just a few questions, just a few quick ones, that's all we're going to do here, to get us through the process of going from an expression like this to an expression like this, where we're all set up and ready to do the logarithmic differentiation. Want to make sure we have that skill down before we jump into the actual process. Okay, so that's what we're going to do here, and then in our last video we're going to look at actually computing logarithmic differentiations. Let's go. So example 1, apply natural logarithms to prepare the function for logarithmic differentiation. So we start by saying I'm going to take the natural log of both sides of my equation. So the ln of y is going to be equal to the ln of the biggest pile of stuff that we could possibly imagine that we'd ever want to apply a logarithm for, until we see the next example, of course. So let's see what we've got here. First things first, this is a product, and I know that a logarithm of a product can be torn apart. So I still got ln y on the left, and on the right I can tear that apart to be separate logarithms. Ln of 3x minus 1 squared, and if it's a product, that becomes the sum of two separate logs plus the, I keep writing limit, and I don't want to write limit because these are not limits, they're logarithms, plus the ln of 10x squared plus 3x minus 1 to the power of 10. Good. Now, the only thing is I still have composite functions there because I've got these exponents, but the beauty of logarithms is they allow us to float those out in front. So I have ln y equals ln of, 2 out in front of the ln of 3x minus 1, plus we're going to have 10 out in front of the ln of 10x squared plus 3x minus 1. So that's what we would do to break that down and separate everything out so that we're ready to perform logarithmic differentiation. Let's do a couple more examples before we call this session done. Apply natural logarithms to prepare this function for logarithmic differentiation. So let's see. Ln y, same thing on the left all the time. Ln y, ln y, ln y. That's going to be equal to the ln of another big pile of stuff. So we've got 4 to the power of x times e to the power of 2x times the tangent of 5x minus 1. Okay, and this is again just a product of a whole bunch of things. So when I separate this one out, I've got ln y equals ln of 4 to the power of x plus ln of e to the power of 2x plus ln of the tangent of 5x minus 1. Okay. And then I'm not going to do much with that last one. I'm going to leave that alone. But the reason I put another one that was just products in there is you'll see in a sec here I can take this x and move it down in front. So I have x ln 4, and really all I'm differentiating when I go to attack that term, it's just going to be a linear function, isn't it? Because that's a constant times x. Plus, in the next one, I've got 2x times the ln of e, which is really nice. That's nice and simple. Plus, I'm going to leave the ln of the tan of 5x minus 1 alone for now. I'm just going to do one more step here. So we're going to call this the ln of y equals x times the ln of 4 plus ln of e, of course, is just 1, so this term is just 2x. That's two linear functions is all I have there. Super simple to differentiate. Plus ln of tan. Now that one I'm still going to have to attack with the chain rule, but at least that's the only one I'm going to have to use the chain rule on here. Everything else is way simplified. If you look at what we started with here, otherwise we would have had an exponential times another exponential times a trig function, where the second exponential and the trig are both chain rules, and all three things are going to be product rules with one another. That's crazy. Logarithmic differentiation. You'll see how it makes our lives a lot easier. In this case, I have to apply the natural log to try and separate this one out, but in this one what I've got is I've got a product in the numerator with some nested business going on there, and in the denominator of all of this I've got another power function with a linear function inside. Yikes. Okay, so let's try this one. The ln of y equals the ln of a whole bunch of stuff. So we've got in the numerator secant squared x. Now, before I go any further, I know that this one is already a logarithmic function, so I might as well get that 6 out of that exponent, because I know for the sake of taking a derivative, which is, remember where we're headed with this, it's easier not to have things in exponents. Constant multiples are nice for derivatives. So I'm going to do that right now and get that taken care of. And then down here I've got 12x minus 7 to the power of 19. And a quick way to do the separation business is if you're having a logarithm of a fraction, then anything in the numerator is going to have to be a positive. So I'm going to have that limit ln of secant squared of x there plus ln of 6 log base 4 of x, and there's some more we can do with that too. And then I've got to subtract the bits from the denominator, and there's only one bit here, so it's the ln of 12x minus 7 to the power of 19. Okay, so a couple more things I can do to simplify this to make it, if I was going to take my derivative right away, make it a bit easier. Here I can take this 2, because that's the secant all of it squared. I can float that out in front. So I've got 2 ln of secant x. So that's not too bad to deal with. Plus, now here I've got another product inside there, 6 times stuff. So I might as well separate that out, because you'll see that's going to be the ln of 6 plus the ln, and that's the only ugly term here really, ln of log base 4 of x. Can't get rid of everything, but still it makes it easier. And then when I do go to take the derivative, if I were to do that here, that's just going to be 0 anyway, because it's constant. And then I'm going to subtract 19 times the natural log of 12x minus 7. Okay? So what I've done is I've separated all that out, and it looks like it's going to be much easier to take the derivative now. So there's some work to do the separating out, but it's a lot less work than what you would have to do for those really gross functions if you're going to try and differentiate them. Let's try one more example here before we roll on to greener pastures. Apply natural logarithms to prepare the function for log differentiation. Same question as before, but different one. Okay, now this one I want you to notice that I've got 2 things down in my denominator. So when I separate this out, we've got to be careful about what we do with those signs. So this is stuff that you should know from your 3200 course about laws of logarithms, but we're just going to be careful about it here anyway, because it's a different context, so we don't want to forget all the things we need to know. So I'm going to start with just applying the log to both sides. So I've got 5x squared minus 4x plus 1, and that's over cosine x times tan squared x. Okay. And so now I've got to try to separate all that business out. So it's still ln y, and it's going to be equal to. Now, when we separate these things out, remember, anything that's in the numerator is going to be positive. So if you want to do this in 2 steps, that's fine. You could say the ln of the numerator, subtract the ln of the denominator. And then when you split the denominator up, they're going to be added, but the whole thing was subtracted. They both get negative signs anyway. Yuck. It's just quicker to say the ln of the cube root, so everything up top, and it's just the cube root of 5x squared minus 4x plus 1. And then everything downstairs is going to get a negative sign. So the ln of cosine x times tan squared x. Nope. Minus the ln. I'm going to split that up now, I forgot. Of tan squared x. Okay. So now for all of that, what I can do is I can simplify a little bit more anyway. This cube root that I see in my numerator, the one that was in the numerator, that's now on top of the 5x squared minus 4x plus 1 can become a 1/3 multiplied in front, because that's the same as the power of 1/3. So I have 1/3 times the ln of 5x squared minus 4x and 1. And there's not much I can do with the ln of cosine. I'm going to have to lump that one and deal with it later. It's still going to be a composite function there, but not very difficult to deal with those kinds of things when log is outside. And then I'm going to subtract, and remember this too applies to the entire tangent. So I'm going to float that out in front, so I've got 2 ln of the tan of x. And so that one is ripe for differentiation now. Okay, so what we did is we applied our laws of logarithms to rip these functions apart into pieces. So there's a little bit to that, but not nearly as much as there would be to actually go and try to differentiate them as they're given. So here's the order in question. Lots of stuff to rip apart there. It's a cube root of a whole pile of things. So good luck with that. I'm going to flip to the solution page for this now. So pause if you want to do that. So there's your solution. So just tear it all apart so that it makes it a little more friendly to differentiate. And then we'll highlight some of the key things that we talked about in this session. So things that we mentioned here were, we had logarithmic differentiation is the technique for finding derivatives. We've got 2 primary uses. It's to differentiate functions that have a variable in the base and in the exponent, like this one. We're going to see some other kinds of those in our next session as well. And it's also to simplify the differentiation process for more complicated functions, like all those other ones that we just practiced with. So they would imply multiple uses of product, quotient, and or chain rules, and we can avoid all of that with log differentiation. The basic idea behind log differentiation is to apply natural logarithms to both sides of the equation, and we then use the laws of logs to break that function into simpler pieces. And then in this session, all we did was practice the application of the ln and the breaking apart, and again in our next session, that's when we'll actually get into taking those derivatives. So I hope that helps. Hope that's a good review of at least how we start off with logarithmic differentiation, and we'll finish that up next time. So good luck studying. If you got any questions, throw them up on D2L. Thanks.